Welcome back to elementary statistics. In this video, we're going to be talking about goodness of fit using the chi-squared test. Right? Goodness of fit is one of several things that we can do based on the idea of chi-squared. Spelling it out, it's the Greek letter xi, which kind of looks like an x raised to a second power. Right? So that's the symbol chi-squared. You'll see it written out, you'll see it in symbol in about equal likelihoods. We've not talked about this distribution in the past, so before I did anything else, I wanted to look at a chi-squared distribution table. The interesting thing about chi-square is that unlike the z-table and t-table we've worked with previously, the chi-square table is not symmetric. It has a normal-ish looking shape here, and then an extended tail. This is a distribution that has a positive skew. It has high outliers. And so because of that, this table looks a little bit different as well. Whoops, wrong button. That's the one I wanted. Instead of just having key values for very low values of alpha, right? 0.005, 0.01, 0.025, 0.050, that's the 95% that we very often use. But it also has the other extreme, 0.995, 0.990, 0.975, 0.950. Because if we are looking at the high end or at the low end, things are going to be different. For our purposes, we're just going to be looking at the things going on at the high tail. So values like the 0.50 column right here are the ones that are going to be a little bit more useful to us in this lesson, but other applications of the chi-square distribution are going to deal with things a little bit differently. All right, so we're looking at that chi-square table, and we're going to be using it in this instance to look at categorical frequency distributions. So in order to talk about a categorical frequency distribution, in order to talk about the goodness of fit test, we need a frequency distribution. So let's just take a look at a distribution with 5 colors, red, blue, green, yellow, and orange, listed in order of decreasing frequency: 32, 28, 16, 14, and 10. That doesn't look like a 10. That looks like a 10. Our goal in goodness of fit testing is to compare the observed results in the sample to expected results from some model. And sometimes understanding what I mean by that can be challenging. I'm going to look at a very simple model in this lesson, but we are going to be forming a hypothesis test. We know the relative frequencies we expect for the 5 different colors that appear here. Maybe we are given those in a percentage table. We constructed a model before we started that said that we had 20% in all of the categories. Each category is equally weighted. That's one model. Or maybe we expected that things were mostly equally weighted, but red was slightly more popular and blue was slightly less popular. That's a different model we can use. And no matter which version we use, we can perform this test. I'm going to use the equally likely model because it is the easiest one to use, but it's certainly not required that that be the case. I do need to find some way of representing what our model predicts is going to happen. And percentage frequencies tend to be a good way of doing that. The null hypothesis here is the claim that our observations are not different from the model, and the alternative hypothesis is that there is a noticeable difference from our model. All right. In this case, our model is that each of the 5 colors are equally likely. So if we accept the null hypothesis, then we have no evidence to the contrary that our 5 colors are equally likely. If we reject the null hypothesis and accept the alternative hypothesis, then we are saying that it is not the case. We have evidence refuting the claim that the 5 colors are equally likely to be chosen. And we're going to do this with a chi-square test, as I said before. In the goodness of fit test, the degrees of freedom for the test is the number of categories minus 1. In our case, in this example, we had 5 categories: red, blue, green, yellow, and orange. Subtract 1 gives us 4. And I'm going to use the same confidence level that I have used throughout this video series. Let's look at a 95% confidence. We're not required to do that, but it certainly works. That is an alpha value of 0.05. So if I come back to my chi-square distribution table, I notice where alpha equals 0.05 is this column right here. And I go down and I find the row that matches up with 4 degrees of freedom to get the critical chi-squared value of 9.488. And I'll jot that down. Now I'm ready to test my distribution. The formula for chi-squared in a goodness of fit test is the sum of O minus E squared divided by E. And I'll talk more about what that means in just a moment. If this value of chi-squared is greater than or equal to our critical value, which in this case is 9.488, we will reject the null hypothesis. If chi is less than 9.488, we'll accept the null hypothesis. I put or equal here, but technically we probably shouldn't, right? Or equal is always a weird case. I have never actually seen that happen where you are exactly equal to your critical value, but it could happen, I guess, in theory, in which case I would suggest continuing the study and trying to get more data. But there's our goal. That's the thing we are looking for. Now, we have this formula. It's a formula involving a summation. And a formula involving a summation is going to behave similarly to the last formula we had involving a summation, which was the standard deviation formula quite some time ago. When we dealt with standard deviation, we had to create a table with a number of columns in it. Right. The first thing I'm doing is just recopying the table that I presented earlier, so we have some space to work with it. And yes, I need all of this space over here off to the side. We are going to be taking advantage of that. I'm going to slightly change the name of that second column. Instead of calling it the frequency, I'm going to call it the observed frequency. This is what we saw in our sample. I'm then going to create a new column called the expected frequency. This is the frequency that our model is predicting. And we gave that as percentages. I need to turn that from percents into numbers. Well, if I add up the frequency of each color in the distribution, 32 plus 28 is 60, 76, 90, 100. It's almost like I designed it that way. N is exactly 100. And if I expected to have 20% of the responses in each of the colors, and I have 100 responses, the math there is very simple, that I expect to get 20 responses on each. Other ways we can think of this. If I didn't have the percentages, if I just said that I expected to see equal frequencies of each, I would take my 100 samples, my 100 members of the sample distribution, I would divide by the 5 different categories available. 100 divided by 5 is 20, and that's another way I could have gotten this, which relies on the fact that I'm talking about equal likelihood. If I wasn't talking about equal likelihood, I'd have to have some other way of conveying what my expectation is. Percents are really nice. take the percent likelihood that you expect for each category, multiply by the total number available, which doesn't have to be quite so easy as 100, but that will give you a expected number likelihood, the expected value of each of the categories, giving us something we can work with. Now, my formula didn't just have the observed frequency and the expected frequency. It had other categories. It was the observed minus the expected. So 32 minus 20 is 12. 28 minus 20 is 8. -4, -6, and -10. We square all of those things. And then we divide each of those things by E. This is where the example that I'm using of equal likelihood makes the arithmetic easier, because in each of these categories, I'm dividing by the same number 20. But it's just take whatever number here, divide by whatever numbers in that column. Right? 144 divided by 20 is 7.2. 64 divided by 20 is 3.2, 0.8, 1.8, and 5.0. It's not the same calculation as standard deviation, but it should feel fairly similar. Working across and calculating this category by category, and then when we reach the end, adding everything up. 7.2 plus 3.2 is 10.4. 11.2, 13, 18.0. Chi-square in this distribution is 18.0. It is bigger than our critical value, 9.488. Again, remember that value just came out of our table. And because it is bigger, we want to reject the null hypothesis. This sample is not representative of equal likelihood. There is a difference between what we saw and what we projected. Or, in other words, coming back to the title, the model we started with of the 5 colors are equally likely is not a good fit for this distribution. That's the idea. I don't want to spend too much time just driving through the mathematics. Working through the calculations on this table is tedious. But again, once you understand how tables work from standard deviations, rely on that skill set to get through this one as well. Before I wrap up here, for discussion, we talked previously about statistical tests on proportions. And the idea of working with a proportion and the idea of working with a categorical frequency table are kind of related to each other. So my question to you, could you use the goodness of fit distribution as a way of working with a proportion instead of using the proportion test that we used previously? If so, how would that work? Does it seem like it would be easier? I will give you a hint. There's a reason that we came up with two different names for tests here, but some people have a preference of one over another. In any event, that's all I have for you here. Thank you as always for joining me. I'll see you next time.